we have a linear production function of AK plus BL. And we're going to use a specific number here just to show the math. And let's say it's 3K plus 6L. So in order to get a certain measure of quantity, it's this relation. So first, how much do we get if we had 9 of capital and 16 of labor? And the other question is, what is the marginal product of capital and labor? Hint again, we have constant slopes. So let's go back to Excel. First question, what is the total production? Well, Q equals, and what the expression tells us is right here, 3K plus 6L. Okay, 3 times the number of units of K is 9, plus 6 times the units of labor, which is 16. That's 123. And these are in units of production or output. Next, what is the marginal product of capital? Marginal product of capital, right? And here, since it's a line, it's easy. It's simply the coefficient in front of the variable. So capital is here. The coefficient in front of it is 3. So that's the answer. And the marginal product of labor, likewise, is easy. What's in front of the L? It's 6, because we have constant slope. So constant slope means that same marginal product for all levels, or all values of K and L. All right, so that's the first exercise. Okay, the next exercise is the Leontief. And this one has, again, given an example here of minimum 3K and 4L. And the scenario we're looking at is how much Q do we get if K equals 9 and L equals 16? And what is the observation we make about the impact of capital and labor variables as they change away from, let's say, this point of 9 and 16? All right, so let's go back to Excel. All right, so let's figure out the output. The output has this unusual characteristic where we take the minimum of two values. So let's specify them. So it's the minimum of, and the first expression is 3K. And the second expression is 4Ls. So let's compute those for the data provided. First is 3 times 9 is 27. Next is 4 times 16 is 64. Therefore, the min of those two is 27. So this is the output. And notice what this means. That means we had wasted L inputs, right? We'll get more to that later on. The other way to do it is to say Q equals, and we could use the function in Excel for a minimum. So equals min, open parens, and we put the first number in, which is 3 times 9, comma, 4 times 16, close parens, and we'll get the same number, right? So that's the same as this. All right. So that's how the Leontief works, is we compute the two factors inside the expression and compare which one's the minimum, and that is our output. So what's the observation about the impact of capital input variables? As mentioned, we kind of overdid it with labor, right? We noticed that there was a point, we only needed 27 from labor. So what is the amount that would get us 27? Well, if we take 27 and we divide it by 4, we will get how much labor we would have needed to get to exactly the same number. So 6.75. So let's just try this again. Let's go 3K and 4L. The 27 is the same because we're not playing around with that, but we are this one. So now if we had 4 times 6.75 units of labor, we would be optimized. What this represents is this elbow, that corner, is captured by the point where we have, so the optimal point is represented by 9 equal to K and only 6.75 for L, and the resulting output would be 27. Right? So in this case, given this basket of choices, we would say, okay, we will make 27 units, but we're actually wasting quite a bit of L because we were using 16, whereas 6.75 would have got us exactly the same output of 27. So therefore, we would choose to go, if we're happy with production level of 27, we would do 9 of K and 6.75 of L. And notice that we cannot determine the first derivative because there's a lot of variation going on and it's not a normal function. So even calculus would fail us in this particular regard. And this is what we can do for the Leontief. All right, the next exercise is using Cobb-Douglas. And here we're going to use a specific example here in the expression. K raised to the power of 1 over 2 times L raised to the power of 3/4. So I know exponents are tricky for a lot of people, so we'll do this one slowly. And the question again is, what if we had 9 and 16? Same input factors as before. And also, what is the marginal product of capital when we have this combination of inputs? And the last question is, what is the marginal product of labor if we have the same combination of inputs? Here's the formula. I just carried it over here for easy reference. What is the output? So Q equals, and now let's put in the expression, equals, and we'll do this slowly. K is 9 raised to the power of, I'll put in parens, of 1 over 2. Right? So that's 9 raised to the power of 1/2 times, that's multiplied, times L, which in this case we're given as 16, again raised to the power of what? Raised to the power of 3 divided by 4. And that result is 24. So this is the output. Right? And although it looks complicated, all I'm doing is using this expression and inputting the two factors provided, which is 9 for K and 16 for L, and just let Excel do the work for us. Next, what is the marginal product of capital? Marginal product of capital. Okay, and it equals, and we're given the formula here, and that's the first derivative. We could have derived that, but let's go ahead and use the formula. The first is A, and that's the exponent, 0.5 times, and then K. In this case, K is 9 raised to the power of A minus 1. So the power is A, which is 1/2, 0.5 minus 1, times L, which is 16, raised to the power of 3/4. 3 divided by 4, close parens. And that answer is 1.33. Next, what is the marginal product of labor? So marginal product of labor equals, we'll take beta, in this case, it's the number of 3/4, 0.75, times K, which is 9, raised to the power of A, which is 1/2, 1 divided by 2, times labor, which is 16, raised to the power of beta, which is 3/4, 0.75, minus 1. And that answer is 1.125. What this means is for every unit of capital at the margin at this point of 9/16, we'll get 1.66 additional product on the capital side, and we'll get 1.15 on the labor side by adding one extra unit of labor. So now we have the idea of the isoquant. An isoquant is a graphical depiction that's quite useful. Iso in Greek means equal, so isoquant means equals quant, right? So what are the combinations of labor and capital such that we get the same amount of output? That's what an isoquant is. So just think same quantity is for one curve of the isoquant. If we change quantities, we need another curve, right? So that's what we're going to do. Let's look at the representation of this in a graph. If we have labor on the horizontal axis against capital, we'll see this is the curve, and this is an isoquant. The quant being 100, and these are all combinations of labor and capital that will get us exactly the same place. It gets us to 100 units of labor. And we can substitute A for B, and we wouldn't really do much in terms of our output. In fact, we get the same, by definition, the same number of units. We'll see later on that the costs are different at points A and B, but for now we're just looking at combinations to achieve a certain output, in which case we're indifferent. Then we notice that the isoquant moves outward from 100 to 200, 300, and these waves just move out further and further because we're now using more of labor and capital, and that should get us more output, which it does. So that's what an isoquant or a set of isoquants look like for a given manufacturing process. What is the marginal rate of technical substitution? That's a fancy sounding term to say if we're on a point on the isoquant and we move a little bit one way or the other, how much would change if we did that change, right? That's the marginal. That's what it means. That's what's that next movement going to get us. And this is represented by the slope. Once again, the slope of the isoquant is the marginal rate of technical substitution. As we go from one to the other, the margin or slope is this rate that we're looking for. So let's see how this works on the graph. So we start with what we've seen before, but let's move now 1 unit to the left of where we were at point A, and what happens to B. All right, so now we see that as we kind of walk on this curve from here left 1 unit on the labor dimension, we end up here on B, which shows this amount of change in the capital. That gives us a slope. So the change in the capital, which is rise, divided by the change in the labor side, which is the run, is -1 here gets us to 1 plus here. So here the rate is -1, marginal rate of substitution, technical substitution for capital and labor. So let's see what happens when we make another change at a different part of the curve. So let's say we're at C and we want to move 1 unit to the left from C. So here, 1 unit to the left from C gets us over to point D, right? So this move has the slope that is different. The slope is 3 divided by -1, because as we go down a -1 on the labor side, we go up 3 on the capital side. So 3 divided by 1 with a minus sign. So it's a -3 as the rate of technical substitution. So we can see that at different points of this isoquant, we will see different rates of change. And we saw this before when we were looking at even a straight line. But here it's even more pronounced because we're on this curve.